All right, so limiting reactants, I know, can be a difficult topic because it's stoichiometry. So one video isn't gonna always be enough. This is gonna help you get through the steps and understand the steps, but I recommend rewatching this and checking out more of my videos that I have on this topic. For limiting reactants, I'd say one of the most important things is knowing that it produces the least amount of product. So you're either going to hear this as a limiting reactant or a limiting reagent. It means the same thing. And I pretty much want to go over just the general concept. We're bringing back coffee, what's new. So I'm going to explain what a limiting reactant is in kind of like a day-to-day situation. So let's say in this case, if it takes like to make a latte, it could take, let's say, 1 cup of brewed coffee, 1 cup of milk, that equals a latte. However, if let's say we wanted to make as many lattes as possible, but we only had, we had like 4 cups of brewed coffee, but we only had 2 cups of milk, and like how many lattes can we actually in reality produce? So in this case, it would have been 2, right? Because we have to have, like, the recipe calls for 1 cup of milk. So I know that this would have been my limiting reactant or ingredient that doesn't allow me to produce as much product as possible. So because I have a less amount of, milk, I am going to produce less of my product or less of my lattes. Make sense?
Yep.
Cool. And then, of course, whatever is left over, the other reactant, or in this case, ingredient, would be called our excess reactant. And then just kind of like to put the terms and everything, whatever the limiting reactant actually produces is then called our theoretical yield. So in this case, our theoretical yield would have been, 2 lattes that we could actually produce. Okay, cool. So now that you understand the concept, let's put this into chemistry. Let's start off with just practicing. This is actually a good practice for us. Practicing building equations, balancing them, and this is going back to naming. So, yeah. So
I thought we did away with that.
We did not. And it's good practice for the final as well. All right, so this question is asking us to write the balance equation for the reaction that occurs when iron 2 chloride is mixed with sodium phosphate, forming iron 2 phosphate and sodium chloride. So we need to go back to naming compounds. Let's just start off with how we would write the chemical formula for iron 2 chloride. Go for it.
Okay, so we would write Fe for iron, and then Cl.
Good.
And then we put a -1 and a 2 plus. Or plus
Perfect.
3, whatever. Yeah.
The Roman numeral tells us the charge of the metal. Perfect. And then let's keep going. Let's balance out the charges and find the chemical formula.
Okay, so we will... I'm trying to remember how you told me to do this. We're multiplying and then adding in the subscripts. So...
Correct, yeah.
So we're multiplying that by 2.
Good, because we want both of these numbers to be 2, but essentially what that means, right, when we add a subscript, that essentially kind of means that we're multiplying 2 by that -1 charge.
Okay.
Cool. And then we never include the charges in the actual chemical formula.
Cool, okay.
All right, and then next it's saying iron 2 chloride is mixed. That tells us, okay, that's our second reactant, is mixed with sodium phosphate. So sodium phosphate is our second reactant. And what is sodium phosphate?
Okay, sodium phosphate. So we're gonna do Na for sodium, and phosphate is a polyatomic ion that we have to memorize. Good. So PO4.
Good. What's the charge of phosphate? Sadly, the periodic table won't save you there. So that one is memory, right? Polyatomic ions and their charges. I know. That one you just have to memorize. It's not going to tell it, on the periodic table. So this is one that we had to know was a -3. And then now with a typical metal like sodium, yes, that one is on the periodic table.
Okay, so +1.
Good. Okay, keep going. How would I balance this?
Okay, so we have to multiply the sodium by 3, so we make it the subscript, so Na3.
Perfect. Awesome. And then next, I'm going to keep going, and it's saying forming. So forming tells us, oh, the products are coming up. So this is our products now. Our products are going to be iron 2-phosphate and sodium chloride. So let's start with iron 2-phosphate.
Okay, so we do the iron, which is Fe, and then the phosphate, the PO4.
Good.
With the charge that we know now.
Yes, which was?
I forgot that fast.
3 minus.
Oh yeah, okay, that's what I was gonna say. Okay, and then the iron, we look at the charge on the periodic table, right?
Not necessarily. This has a Roman numeral, right? The Roman numeral is our hint that it tells us the charge of the metal.
2 pluses.
2 plus.
And then we crisscross.
Correct. Then we crisscross, exactly. This 2 goes here, this 3 goes here. So this is Fe3, and then parentheses PO4 with a 2 subscript on the outside. Perfect. I'm going to say, since this was forming, that means that was my product. Now I'm going to get the second product. So sodium chloride, what's that?
NaCl.
Perfect. Easy enough. Cool. Because Na has a plus charge, Cl has a minus charge. They're balanced. We're good. Okay, next is balancing this actual equation out. So I know I'm combining an insane amount of things all together, but this is good review, and this is a common question. So let's just start off with balancing. What's the first thing that we want to do with balancing?
Okay, so we have to start out by writing out all of the elements, and then we're going to start balancing. So we'll count how many we have.
Perfect. Go for it.
Okay, so for iron, we have just 1, and then there's 2 chlorines, 3 sodiums, and just 1 phosphate.
Perfect. Next side.
And then we have 3 irons, 1 chlorine, 1 sodium, and 2 phosphates.
Perfect. Okay, what do you want to start balancing?
Okay, so I guess we can just take it from the top. So, for the iron, we need to get to a 3, so we will put a 3 in front of it. Yep. And then that multiplies it by both of those. So our new iron has 3, and then the chlorine will be 6.
Exactly. And then everything else stayed the same. We didn't change anything. Cool. What's next?
Okay, so next we're going to do our chlorine. So we need to get to 6 now. So we'll go over to the product side and multiply the NaCl by 6. And so that changes the Na and the Cl to 6.
Perfect. Okay, keep going. What's next?
And then the sodium. Oh, okay. Sorry. I just kind of realized like what happened. Okay, so you can cut that out. Okay, so for the sodium, we need to get to 6. So if we go over to the reactant side, we can multiply or put a 2 in front, and so that will make the sodium 6, and it will make the phosphate 8. Wait, no, it will make the phosphate 2. That 4 doesn't go along with it.
You caught yourself, exactly, good. And then we're balanced.
Yay, okay.
So, yay. Cool, so I'm gonna just remove this. We're gonna need this formula. This formula is really important because it is gonna help us do the stoichiometry that is part of limiting reactants. So this was just the first step. Definitely, I'd say practice. Naming compounds, balancing equations, all of this will come up again, as you can tell. So the next step is to actually find the limiting reactant. So this question is telling us if 23 grams of iron 2 chloride reacts with 41 grams of sodium phosphate, what is the limiting reactant? And it also asks how much sodium chloride can be formed. So this is actually asking for 2 separate things. It's asking for the limiting reactant, And it's actually asking for the theoretical yield by it saying how much sodium chloride can be formed. And I'll explain how I can just tell that that's what it's asking. So looking back at the formula that we just found, the balance equation that we just found, we know that sodium chloride is a product, right? So because we know that that's our product, this is asking us how much, like kind of like back to the lattes, it's saying how many lattes can we actually make from the limiting reactant? Okay, so that's the concept here. So the first thing we want to do is to just find the limiting reactant. How we do that is we're going to take the grams of each reactant that's given, and we have two reactants, right? And we were given the mass of two different reactants. And then we're going to make our way to the grams of the product. So this is going to be a long process, and it's going to be a bit more of stoichiometry. So we can't just magically go from the grams of a reactant to the grams of our product, right? There's no one conversion factor that can take us there. So instead, we have to go through kind of a series of steps. And this is what it's always going to be whenever we're going from the grams of our reactant to the grams of our product. So we're always going to go from our grams of our reactant to the moles of our reactant. Then we're going to get to the moles of our product. And then lastly, we'll be able to get to the grams. Let me just make some room.
So is this the same every single time?
Yes.
So I can just like kind of memorize this process and then it'll be for every limiting reactant, or?
I never want to say memorize.
Okay.
I always want you to understand. Yeah, because...
but like the steps will be the same, right? Like
the steps should be the same, correct. The steps should be the same if you're given grams. So if you're starting off with grams of your reactant and it's asking, you to find like how much of your product is formed, then yes, you'll go to grams of your product. However, if it starts off with the moles of your reactant, then you would have just like skipped the first step and you would have started here.
Okay, I see. Yeah.
Yeah. Cool. So in this case, I'm just going to apply this to everything that we have. Instead of our first reactant, I'm going to do this for our first reactant, which is, we said iron chloride. And I do like just putting whatever reactant that I'm actually like doing this for on top just to separate everything. You'll see why in a second. But I'm actually going from the grams of my first reactant to then the moles of my first reactant to the moles of the product. And here we have two different products. If you weren't told, how much sodium chloride can be formed, then it wouldn't have mattered which product you would have chosen. So as long as both of the reactants that you're taking go to the same product. So meaning as long as you just like commit to iron, phosphate, picking that one for both of the reactants, the process, then that would work. Does that make sense?
Yes.
Kind of. Okay. I can reiterate it once you see the whole steps.
Yeah, once I see like the next one, but I think I get what you're saying.
Yes. Yeah. Okay. But because this already asked me, how much sodium chloride am I going to form, I know that the product that they want is sodium chloride. So I'm actually going to sodium chloride.
So we'll use that for both, right? Okay.
Correct. Cool. So awesome. I'm just going to plug everything in. The first conversion factor that we're going to use is going to be the molar mass of iron chloride. And let me just set this up. So 23 grams. I haven't found what the mass is, so if you want to do that as well. Just going to do that here. Cool. Just 35.45 times 2. Okay, and then all those added, right?
I need to get a giant periodic table because whenever I'm looking at like the little teeny numbers on this, it's so hard to see.
Right.
I got the molar mass. So I know you know how to do molar mass, but cool. So that's what we would get for the first part after we added all the individual masses of our elements together. Next, that was our first conversion factor. Now that I'm here at moles of my reactant, now I have to do a mole to mole ratio. And something to kind of just note, so this is stoichiometry, where this portion, basically, like how you know to do a mole to mole ratio, is the fact that you want to change the compound. We start off with one compound, which is iron chloride, and now we want to change the compound to sodium chloride. So to be able to do that, you need to use a mole to mole ratio from the balanced equation, and that's why it's so important. So I would look at the coefficients in front of whatever I'm looking for. So the moles of iron chloride are 3, and I'm going to place that on the bottom. So 3 moles of iron chloride, just so these units could cancel. And then next I'm going to look at sodium chloride and the coefficient in front, which is 6. So that's where I'm taking these numbers from, is from the balanced equation. Make sense? Yeah. And then now that we're here, we're at this step, we're at moles of NaCl. I'm going to again, so I'm just going to just show this real quick that this was a mole to mole ratio. And then the third conversion factor is just using the molar mass again. Whenever we're going from moles to grams or grams to moles, we use the molar mass of whatever compound we have. So in this case, it's NaCl. So I'm going to just find this again, adding up everything, all the masses of chlorine and sodium. I think sodium is 22.99. Yeah. So 15, you're just like, I'm just gonna let you do your thing.
I'm writing down like the steps because I know you're gonna give me practice problems.
That's true.
So I'm just
trying, you know it's coming.
I'm trying to write down like, okay, first step, molar mass, second step, the ratio.
Yes, that's totally fine. I'm glad you're doing that. NaCl, cool. Okay. And then you'll see that all of our units cancel to give us what we want, which is the mass of our product. So now I'm just going to multiply straight across and then divide by the bottom. So I'm going to multiply 23 times 6 times this value, and then I'm also going to divide by these two multiplied. So let's see what this gives us.
I haven't used the calculator in a while because everything else we've been doing hasn't really needed it.
Lewis structures, yeah.
Yeah, Lewis structures. Those were a good time.
Sadly, it's over now.
I know. Now I have to do real math again.
Okay. Let me know if you got this.
I'm still calculating the bottom. Now I'm dividing. Okay. Okay, 22. We're 21.2, yeah.
Cool. So I would say, and one thing I'm also going to mention is just the fact that I'm actually even going to round this down a little bit more. This is only 2 sig figs, so I only want 2 sig figs, so I'm just going to say this is 21.
Okay, I see.
Yeah. So, okay, that's the first part where I'm saying, all right, this first reactant here produced 21 grams of, here, I want to put them like all together. I'm just going to put it over here. Okay. This first reactant produced 21 grams of my product, okay? And I'm gonna do this all over again. So let's redo this for the second reactant, and you do this for each reactant. So luckily there's only 2. And typically there's only 2, but all right, I'm gonna do this again, and I'm just going to replace everything that I need. Okay. Come on. All right, so the next reactant, if I can delete things fast enough, the next reactant that we're going to do this for, and you're really going to see this same sort of setup every single time. The next reactant is our sodium phosphate. So I need the grams of sodium phosphate. I'm then going to use the molar mass of sodium phosphate to then get to the moles of sodium phosphate. And then it's the same process again, mole to mole ratio to change the compound, and then our mass of sodium chloride. So I'm going to start off with the 41 grams of sodium phosphate. I now need the molar mass of sodium phosphate. So I'm going to do this real quick, add everything up. This is 22.99 times 3 plus phosphate's mass, which is 30.97, plus 4 times 16. So I get 163.94 grams of sodium phosphate. That's the molar mass. And then for every 1 mole of sodium phosphate.
And when you're doing the phosphate molar mass, you're just doing like phosphorus and then 4 oxygens?
Correct. Yeah, I'm multiplying everything. So I just want to show it just for everyone as well. I'm multiplying, every single subscript with the element. Phosphorus was 30.97, and then oxygen was 4 times, that's 16, and then multiply, add everything together, and then that gave me that 163.94.
Yes. Okay. Cool.
Cool. Next, so we're gonna be at this step where we're changing this to moles of sodium chloride. So I need to use the coefficients again, and I'm going to look back and see, all right, sodium phosphate has a 2 coefficient. So this is 2 moles of sodium phosphate. I just used again the periodic table. I just used again the balanced equation. Goodness. And yes. Next, this is basically the same exact setup, right? We're going to go again to grams of NaCl. So, okay, I see that grams and grams cancel, moles cancel, moles again, and we're left with what we want. So same process. I'm going to multiply straight across, divide. And let's see what this gives us. Okay, and then I'm going to round to 2 sig figs. So I got 43.8, but I'm going to round up to 44 grams of sodium chloride.
Perfect, that's what I got.
So perfect. Cool. So I'm going to just kind of remove all of this and just show you. I'm going to separate this. And then let me put that, our second reactant produced this. So this is both of our reactants and how much product they actually produced. Now, the reason why I like to separate this at the end or even in the beginning is because after you do all this math, typically I've seen students say, oh, the limiting reactant is NaCl. And it's like, no, that's the product, right? That's not a reactant. And it's just because you forgot kind of what you were doing in this, you got lost in this whole process. So it's important to know, all right, this is the reactant that I started with, and then I'm picking from these two to say whether or not they're a limiting reactant or not, because they are reactants. So we said that the limiting reactant produces the least amount of product. So which one of these reactants produce the least amount of product?
The first one.
Yes. So this one is the limiting reactant because it produced the least amount of product. And then this must have been the excess reactant because it's what's left over. Now, the next thing is, this is saying how much sodium chloride can be formed. So the theoretical yield is whatever our limiting reactant produces. So what do you think is our theoretical yield?
I'm thinking maybe we add them, but I don't know.
So we wouldn't add them.
Oh, okay.
So what did the limiting reactant produce? Like how much product did the actual limiting reactant produce after we found
the 21 grams?
Number.
Is that what you're talking about?
Exactly. Not a trick question. Yeah.
Okay.
Yeah. So I know that my 21 grams is the theoretical yield. So theoretical yield. Now, what is this 44? It's nothing. It's already served its purpose. The whole point of that 44 was just to figure out what the limiting reactant was. So we do nothing with that 44, erase it from your mind. That is not what we can actually produce. What we can actually produce is the 21 grams of NaCl. Okay. So that's what answers this question. And then I'm going to keep going. It is going to be important to know what your theoretical yield is, how to find it, and just like, I'd even say like some of the common words that they use. So they may say like in this case, they said how much sodium chloride can be formed. They could have said, what's the maximum amount of product that you can form? And it's not going to be the largest number. That's not the case. It's always going to be whatever the limiting reactant actually produces. All right, so for every single time they're asking you that, they're really referring to the theoretical yield. Does that make sense?
Yes, good to know, because I would be the person who would think it meant the bigger number.
Right.
Yeah.
And even like they'll say it as like maximum, minimum, like all these different things to try to trick you. They're all talking about the theoretical yield.
Okay.
Yeah. So the next thing is talking about the excess reactant and how much is actually left over. So this is said this way. It's saying how much of the excess reactant remains when this reaction has gone to completion. In other words, how much of our excess reactant do we have left? And how we do this is we're going to use our theoretical yield. So we take our theoretical yield, which was 21 grams of NaCl, and now we're going to basically go from the grams of our product to the grams of our excess reactant. Okay, so that's how I want you to think of this. This is our product that we found, specifically the theoretical yield. And then now we're going to make our way to the grams of the excess, whatever the excess reactant was. So I'm going to do this again. It's pretty much almost the same sort of concept, right? We're going to go to moles of our product. It's now like reversed, but we don't have to do this twice, thankfully. This guy wants to slide over. Okay. And then this is the moles of our excess reactant.
Okay.
All right. So I'm still going to let me bring back that balanced equation because we will use it again. Cool. And same sort of concept. I'm now going to go to the moles of the product using the molar mass that we previously found. So let me set this up. So I put the grams of NaCl, and I'm just going to take it from what we found. Actually, I deleted it. Never mind. Okay, I have to redo it. So that was 22.99 plus 35.45. I used to have a lot of these memorized back when I was like tutoring every single day. It's like coming back to me again. Okay. So cool, that was 58.44, and this is for 1 mole of NaCl. Awesome. Now the next thing is going to the moles of our excess reactant. So we said that our excess reactant was this one, was sodium phosphate. So I need to go to the moles of sodium phosphate. I'm going to look again at the balanced equation and say that this is 6 moles of NaCl. And then now I'm trying to get to the excess reactant. So 2 moles of sodium phosphate. And last, I would use the molar mass of the excess reactant to give me the grams. So I'm going to do this again, just finding this again. This was what, 22.99 times 3 plus phosphorus was 30.97 plus 4 times 16. So it was this 163.94 grams of this. Okay. A lot of stoichiometry.
Yeah.
So I would cancel everything out and I'd see that, yes, I have what I'm looking for, which is the grams of my excess reactant. The next step is to just multiply. So I'm going to multiply everything out, doing this first 21 times 2 times all of this, divided by the bottom multiplied, so these two multiplied. And I would get 19.63. I'm going to round to 2 sig figs since this starts off as 2 sig figs. So I'll round up to 20. Which technically isn't 2 sig figs.
Oh, yeah.
But I still would round up. So I would still round up regardless. I'm not going to change this to scientific notation, which is what you would essentially do. You'd move this over once, like if you're really being a stickler, but that's not what we're looking for right now. And you'd move this, over once, so negative, actually a positive one. If it was truly scientific notation and you needed to end with that answer, but we're not ending with that answer.
Okay.
Does that make sense? Yeah. I'm just going to say 20 for everybody who wants to be a stickler with sig figs and call me out. So if you really want it, you'd put 2.0 times 10 to the first. Okay. And this is grams of Na3PO4. All right. Next step, finally, we're almost done, is to actually find the leftover amount of the excess reactant. So what we do now, what we just found, what was actually used in the reaction, okay? So think back to the lattes, and we had 2 cups of milk and we had our brewed coffee. So what was actually used was 2 cups of brewed coffee to make 2 lattes, correct? Mm-hmm. This is what we're saying here. This is the used amount of our excess reactant. So now we're trying to figure out how much is left over. So I'm going to take the original amount that they gave me in the question, which was 41. So I'm looking at this. So 41 grams of sodium phosphate. That's what I started off with. And I'm here. So I'll say, okay, I have 41 grams, and I'm subtracting this by what I just found, so the amount used, which was 20 grams. And then now, subtracting that, we don't need a calculator here, right? This is just 21 grams that is left over. So our answer here would have been that there's 21 grams of Na3PO4, and that's how much is left over.
Okay.
Make sense?
Yeah, this is just really...
It's a lot of steps.
Something.
I know. I trust me. I know. This is why we're covering it and going over every single thing you may see. So I put out the steps. This is going to take practice, as everything does. But we have one more type of question that they could ask with this section. Okay. So I'm going to keep going. I know. This is these questions tend to be multiple, when they have multiple parts, A through D. So that's something to be aware. This question is saying, if 16.1 grams of sodium chloride are formed in the reaction, what is the percent yield of this reaction? So you've done percent yield, most likely in lab already. That smile tells me yes.
Oh, so, no, I'm laughing at percent yield is where it's at.
Oh my gosh.
I love that.
Okay, I'm glad. I'm like, this is going to be nerdy or I don't know, dorky.
No, that's amazing. I'm going to remember that.
Okay, cool. Awesome. So that's how I remembered it. I laughed when I thought of it. And yeah, so yeah, that's the trick for what this is. It's to remember the formula. So you never forget the formula. Percent yield is where it's at, correct? Cool. So besides the formula, you have to understand how to identify what the actual yield is and what the theoretical yield is. So we already found in this question what the theoretical yield is, right? So going back to what we found that 21 grams of NaCl was produced, from our limiting reactant. So that is our theoretical yield. So your theoretical yield is always going to be found using stoichiometry. It's whatever your limiting reactant produces, and of course we do this by stoichiometry. So okay, I know my theoretical yield is 21 grams. Awesome. Next, I'm going to see in this question, this actually tells me what the actual yield is. It's telling me that it's 16.1 grams of sodium chloride. So great. All I have to do is plug it into the formula, and you'll know it because of this adorable memorization tip. And then you multiply by 100 and you found your percent yield.
Awesome.
Cool. And then I would just, I would say I'd round up since everything, actually I'd even just say, this has 3 sig figs, so I am going to round to 3 sig figs. So I'll just, actually right here, I'll round up to 76.7%. Because this is percent yield. Cool. I think percent yield is probably the easiest one if you remember the formula compared to all the stoichiometry that you did. But if you don't know the theoretical yield and you don't get that correct on your stoichiometry portion of this, it would be wrong. So of course, the first step of even finding the limiting reactant is going to be extremely important.
If there's specific steps that aren't making sense, then please go back, rewatch certain parts, and write those steps down until you really can get this down. Don't memorize, actually understand what's happening in every single step.